This right here you can kind of ignore, but the basic thing is like with this file that we're going to read, we're getting the contents out of it and then sending the contents to something that'll print them. So then over here in, this is GHCI, the Haskell interpreter. Haskell is mostly a compiled language, but it also has an interactive shell like Ruby or Python, or with JavaScript, it has the console, that sort of thing. So I can put that in and it'll read in this temp file and print out the contents, which are hello world and testing 1, 2, 3. So like in my own code, when I'm writing stuff with anonymous, rather when I'm writing a function that takes an anonymous function, a bunch of the time it's that I'm writing a bunch of similar code to, like, I don't know, get something from Vault or whatever. And you can kind of extract out the boilerplatey bits into a helper function that takes in an anonymous function or few that have the actual meat of what you're doing. So you can make your code a bit more shorter and repeat yourself less doing that. So, I mean, that's also kind of what you're doing with like map. Map is similar to doing a for loop, but you're extracting out what you're doing inside the for loop, and you don't have to repeat the actual code of the for loop, which means that you're not going to have a fence post error by mixing up what the bounds are. And it's something that's entirely a library function. You don't need to wait for the authors of the language to implement for each, like you had to in Java for like 10, 15 years or whatever it was. So another useful function is something called reduce, which also kind of captures another notion of what you might do in a loop. And so what reduce does is it takes an array that has a bunch of things of type A in it, and then it takes a function that takes a B and an A, and oh, this is actually wrong. It should be a B, comma A to B. It takes an initial B and it returns a B. So for example, if we want to sum everything up in an array, we can call reduce, and then so the first thing is the accumulator. That's everything that's been reduced so far. And then we have the current element in it. And then when you're adding things together, 0 is the identity element, so we can pass that in. So what this is essentially it's 0 plus 1. We evaluate that, and then we pipe the result of that to plus 2, and then plus 3, plus 4, plus 5. But so in this example, the kind of thing that we're returning is the same kind of thing that's actually in the array. We have a function that takes 2 ints and returns an int. But you could also have it where, for example, this is an empty set, and this right here is something that takes a set and an item and inserts it into the set, and you could use reduce to turn your array into a set or a binary search tree or something like that, inserting everything element-wise, or essentially do almost anything else. Reduce is kind of ridiculously powerful in terms of the kinds of things that if you wanted to, you could compute with it. So does this make sense so far? So when we add 1 plus 2 plus 3 plus 4 plus 5, we should get back 15. And indeed, we get back 15. And then another thing that I'm going to gloss over a little bit, because it's, so there's another function that's useful. It's less obviously useful when you first get started, but is something that I use a ton, is flat map. And so what flat map does is it's similar to map, but instead of returning a single b, you return a, if it's an array, it would be an array of b's, and then you get back an array of b's. When you're talking about other things that you might have flat map on, in the, in the example over here, this is actually a flat map operator. And this right here returns in IO of string. So it would be, in that case, like in IO of B. Or if like you're working on like a parser sort of thing, it would be like a parser B. But probably going over your heads a little bit. But this right here is kind of a gee whiz sort of example. Actually, this right here is kind of a simple example. So if we have the list 1, 2, 3, and then we flat map over it with a function that takes each element and expands it to the list x, 2x, 3x, we get 1, 2, 3, 2, 4, 6, 3, 6, 9. And so if we do this, we have range, which is 1 to 10. And then so if we call flat map on it, sorry. I'd fix that at some point. I might not have committed the fix, but so basically what this will do is it'll return all of the Pythagorean triplets, that have numbers less than 10 in them. And that's one pattern that you will see a bunch in kind of a Haskell style FP, is like repeatedly calling flat map on stuff. And then finally at the end, returning like a single element array, or in this case, we're kind of filtering out the ones that don't have anything in it by returning the empty array there. Looks like we might have lost Brian. So here's kind of an interesting example. So when you sort in JavaScript, you've got a function that returns 0 if the arguments are the same. Then you'll want to return a positive number if the first is greater and a negative number if the first is smaller. And it'll use that to sort the elements into order. So it won't flip things if they're equal. So it's a stable sort. So this has kind of an interesting structure because you can contramap over this ordering. So that is to say, with map, we had a function from A to B, and we got back an array of A's, array of B's. In this case, we have a function from B to A instead of from A to B to get back an ordering of B's. So what does that look like? So to order numbers, if we want it to return 0 if they're the same, x minus y will do that. And then if it's a positive number, if the first is greater, again, x minus y, if y is less than x, is going to be some positive number. And it'll be negative if y is greater. So that's a nice ordering on ints. And then if we want to, say, take that ordering on ints and borrow that to generate an ordering on arrays, ordering them by just their length, we can call contramap, where we take an array and we turn it into an int, and then the underlying thing, when we compare, we have this x minus y there, so that'll compare the lengths and return it. And then we can borrow that again to turn our ordering on lengths into an ordering on like characters by the number of things that they have in their inventory or whatever. So it's kind of compositional because you can take any ordering that you already have, and then if you can take something that you can turn into the thing that you have an ordering on, you can sort that thing. So kind of and I suppose I should also mention that the reason why I call it contramap is because instead of taking the A to a B, it takes a B to an A. And that's a little bit reversed from map. So instead of being what a computer scientist would call covariant, it's contravariant. So people just borrow the contra into there, which is kind of an odd bit of it's an odd bit of jargon, but so this should work there. And then I should be able to say, int ordering there, and then get the length ordering. So you'll see here that it, flips the location of the 2, 3, and 2, 3, 4. So it is in fact now sorted. So kind of the nice thing with having the contramap there is that it allows you to take an existing ordering and use that to generate a new one based off of whatever ad hoc thing you've got. Like, for example, if you have a bunch of characters that you want to sort by their name or whatever, you can contramap over the string ordering to get the characters by name ordering or whatever. So does that make at least a little bit of sense to people? Or is that kind of going over people's head a bit? Makes a little bit of sense, Zach.
No, it's a little over my poor security engineer head.
You can basically ignore this invert thing. That's just kind of another way of manipulating and ordering. Basically it's just like a class around the function that JavaScript uses for sorting. So let's see. So for another little bit of jargon, a free variable is a variable that doesn't appear inside of whatever expression you have. So for example, if we have the expression var add y equals function from x to x plus y, y is free, whereas x is bound right here. And so if we say like var 1 is actually so we can say this. So this right here is actually two anonymous functions. We can say something of 1 and then 2, and that'll add 1 and 2 and return 3. But something 1 returns a function that takes in x and adds 1 to it. So the free variable is with respect to an expression. So then this expression here, y is free, but with respect to this expression here, the greater expression, y is bound. And free variables are important in programming because of a feature that is commonly associated with anonymous functions called a closure. And a closure is basically the way that an anonymous function closes over the current scope. So it captures things that are currently in scope so you can return, so basically, like with here, something 1 is, let's call it var add 1. So we can say add 1 to 2, and that'll give us 3, etc. So this is kind of closed over whatever the y is. So it's, what did I do there? I want to go back to the console there. There we are. So it's kind of like an object where it has state that it's bringing around. Kind of another interesting example where I don't know if you guys have taken calculus. I know Lois has. But so actually, have you guys taken calculus? Okay.
Yeah, I haven't, and I'm happy I haven't. So,
so one of the first things
the best.
that calculus introduces is something called a derivative, which is basically the slope of a function. You can think of it. And so the definition of a derivative is that it's like f of x plus h minus f of x over h, where h is some kind of infinitesimal thing. So kind of the fun thing that we can do here, so in calculus, the slope, rather in math, the slope of 2x is 2, right? It's just kind of, it has a constant slope. It's a line going up at a rate of 2. So what we can do here, so the slope of 2x at any point on the function is the same. And we're doing this numerically, so it's not exactly 2 just because, floating point. And the fact that we're not using an infinitesimal number. But so here we've actually closed over what the function is that we're applying. And then, so this should be more fun for Lois, probably. But then if we have like the slope of x squared, so the slope of x squared is 2x. So if we put in 2, we should get back about 4. If we put in 4, we should get back about 8. If we put 8 in, we should get about 16. And we can do like the first couple of months of calculus problems numerically in like half a dozen line of code. So
or just do it in my head. Calculus.
Yeah, I mean, like derivatives are much easier than integrals, but it was just kind of a cool example that I'd come across a while back. And there's an idea floating around that objects and closures are kind of essentially the same thing. And this koan here is floating around the internet. Apparently it was written back in 2003, but it's, objects are merely a poor man's closures, and closures are a poor man's object. So that's something that had kind of gone over my head for a while, but one thing you can do with anonymous functions is kind of emulate an object with them. So with this, we have a function that tracks an average. So in order to calculate an average, you can calculate that by kind of accumulating up the total that you've seen of things. So if we went back to like here, if we're trying to calculate the average of this array, you could do that by adding this up. So you have 15 as the total, and then you've seen 5 things in there. So then at the end, you can divide 15 by 5 to get back that the average item in there is in fact 3, right? So here we've got an object where, so we have the function average that has the total and the count that we've seen. And then that returns something that takes the method that we want to call on this closure, which if it's the total, we'll return the total. If it's count, we return the count. If we want to actually calculate the final average, we'll return the total divided by the count. And then if we have two of these average objects, we can combine them, where we add the total of the first with the total of the second, and the count of the first with the count of the second. So the reason that you might want to do this is, suppose that you've got a distributed data set that you're trying to calculate stuff on. You can calculate on one machine what is the total number, or rather, what is the total, the subtotal on that computer, and what is the count of things that it's seen. And you can do that for all of the computers in the data center that have your distributed data set. And then they just have that little summary thing that they need to report back up. And then they report that back up to some computer that takes those for the data center and adds them together. And then if you have it in multiple data centers, you can take it across the 3 or 4 data centers that you've got. So you can kind of, it makes it easy to parallelize this in a tree structure. And kind of the nice thing about this in a mathematical sense is that this has an identity element, namely that we've seen nothing and it has a total of 0 in it if you have no data. And then also that it doesn't matter what order you calculate these in. It's all associative and commutative. So it's very nicely behaved in a mathematical sense. And so you can have this function toAverage here that projects in variable x into this average structure. So you can do this with most kinds of calculations that you might want to do. Anything that with the average, it's the total over the count. If it's the harmonic average, you need to track an additional thing and that sort of thing. So it's kind of a fairly general technique of calculating all of the kinds of statistics that people usually care about by projecting the numbers into an intermediate structure that tracks all of the things that you care about. And so with the simpler thing to do is just to do this as an actual object in JavaScript. It's you have the total and the count, and then this, you set everything the way that you normally would in a traditional JavaScript object, right? So, and then kind of so we can put that in there, and that should work. And then what we can do is say something like this. So we have our array of elements, or, logically it could be in some kind of distributed data store, that sort of thing. We map toAverage on it, or over it. So we project it into the things that track the total and the count. And then for each of those averages, we add them all together. And because this is just on arrays, it's going to do that from left to right, and it's not even going to do anything with streaming. I had worked right out of college at a place that had gotten functional programming in the door by doing this sort of thing, streaming, replacing a Java code base that calculated the like average and harmonic average and all those sorts of things like in memory into something that used very little memory and was very fast and, you know, actually a constant amount of memory because it was streaming. Yeah. And apparently, and so we can run this over here now. And that should return 3, which it does. So this thing here in mathematical terminology, average forms a monoid, which is a something that you don't really hear about much from imperative programmers, but it's something that a ton of useful things form monoids. That is to say, you can combine them together and there's an identity element and you can rewrite the parentheses on it. And so it's a really simple thing that turns out to be just powerful enough to do a lot of useful things over like any kind of monoidal thing. So like you could write something that calculates statistics given any monoid, where like average is a monoid, you can make a monoid for harmonic mean or the mode or something like that. But that might be a bit too much into the jargon again. And that is as much material as I had prepared. Questions? Did I go too quickly over things that you want to go back over in a bit more detail? Or what? Did that just entirely fly over everyone's head?
Very close to flying over my head, but I thought it was very good. And, you know, just getting exposure to these things helps pick it up, you know, over time. You just got to keep seeing it and looking at different things. So,
like kind of the main thing is just like using map a lot for things and like trying to figure out when you can use reduce for stuff. Both of those are kind of very powerful functions.
yeah, one thing I'm very sure of. So it looks like you're using reduce here. Accumulator and current, they're parameters there, right? Or
Yes.
Okay, because I'm not sure like what the variable value of those parameters is and how that's kind of going through and working there.
It's very similar to recursion here. So it uses this function repeatedly. So let's see here. So we have something like adder equals that. So we can say like adder of 0, 1, right? And that'll return back 1.
Mm-hmm.
And then we can say adder of 0, 1, 2. And likewise 3. So The first argument with the accumulator is, so the first time it gets past 1, then, so this gets reduced to adder of 1, 2. So let's say that we're evaluating this, right? So this can be simplified to that, right? These are semantically equivalent. And then similarly, we can go in and do that. And then at the next stage, where it would be like adder so at this, it'll go in, and that's now 6. So it's it has the function, and it keeps, it's basically like a for loop that's applying the function at every step and getting the new accumulator and passing it back in the next one. So we could actually, let's see. I don't write that much JavaScript, so it'd be like I in range there are back equals you would first have a var ack outside there, and then you'd have like var temp, no, yeah, accumulator equals adder ack I, something like that, right?
Mm-hmm.
And so it's, you have the function and it gets applied a number of times with whatever the thing that you're accumulating is. Whether, like in this case, it's kind of trivial because it's a number. In other cases, it might be some kind of data structure that you're building up, where you're passing in whatever the initial value of the data structure is.
Okay, I think that helps, you know, at least make it a little bit less confusing. So it definitely, it was a good explanation. You know, just at first sight, it's kind of hard to see how the calculation is being performed there, but now I guess it kind of makes more sense.
Yeah. And so the one thing in JavaScript is, like, it's untyped, so the documentation for it kind of handwaves over the types a little bit. I find like generics and kind of following the types makes what these things do a lot more obvious. And particularly with a lot of this sort of code, in a language like Haskell, which doesn't have quite as many escape hatches from the type system, map kind of the only thing it can possibly do with, or given the type signature that it has, is apply that function repeatedly to the input list. And there's only really one implementation for that. Actually with map, there's multiple implementations that would compile, but you can say some other kind of things about it, kind of for free, given the type. There's other things with generics in Haskell that, like, there's only one implementation for this, so it's kind of trivial in that sense, and kind of like following the types. It's kind of like having toys where, like, you know, you can't put the round peg into the square hole. Like, you have a single round peg and a single round hole, so it can only go there. See, how about you, Lois or Zach or Lana? Anything unclear or questions or anything?
Many things unclear, but
So what's the first thing that's unclear?
There was some I mean, honestly, like my there was no scrappy security engineer Python scripts to look at. Like that's my level. So this was a little above where I am in terms of programming. Like, there were mentions of like memory efficiency and why something is better than another thing. So,
I mean, like, so what the main thing for being better, like, if you're gonna do an object, just do an object. Like, this is verbose. It's, I mean, it technically works. Like, you can do it, but it's very much like there's no real reason to do it. You can, like, they are in a sense equivalent, and like you can have an object with just a single method in it, and then like pass those around, and that's equivalent to having a function. But
yeah, I don't think I'm the right audience, just to be frank. Like, when I hear objects, I like, there's like a class, like you should have like the word class should be somewhere, and I didn't see that anywhere. So
so JavaScript syntactically is kind of weird. They added the class keyword very recently. And so historically, the way that you made a object is you just have like a freestanding constructor that has, like, it's called function, the constructor name, average, and then like you set everything on that object. So this is just like JavaScript syntax is kind of bizarre because actually, do you know anything about the history of JavaScript?
I know. I mean, I can talk about like cross-site origin policy and some cross-site scripting stuff, and
So
it's not Java.
I know a little bit about the history of JavaScript is that it was created in like a week.
Oh, okay.
I think it was more like, it was less than a week. But basically what happened was at Netscape, they wanted to have some kind of scripting language for people to use. And the programmers were debating about like Scheme and Python, maybe Ruby or Perl, Tickle, or some other stuff. But like some pointy-haired upper engineering manager said, you know, Java is this hot new thing. Whatever we do has to look like Java. So they took like a bunch of scheme semantics and like some self semantics and some other stuff, put it in a blender, slapped a C-style syntax on it, and upper engineering manager says, yep, I literally cannot tell the difference between this and Java. And this is good. So,
I'm sensing from your tone that it is not good.
I mean, it's a better language than you might expect given like the circumstances it was created under. But it's got a lot of warts.
Gotcha.
As a language. Like, it's not a bad language by any stretch of the imagination, but like it's got a bunch of odd stuff that like you wouldn't be surprised to find in the first programming language that someone created of this sort.
Okay.
Like, it does have some nice stuff in it, and don't get me wrong. Like, they have improved it over the years, but it's the kind of language that someone threw together because their manager said that they should probably make something that looks like this. And he was like, how can I slip in the stuff that I like into it?
Gotcha.
So
there's motorcycles going by.
Yeah. So this right here, I mean, it's not really that important. It's just the way that JavaScript traditionally works. See, was there anything that you guys had found confusing, Lois and Lana?
Yeah, I'm good.
Okay. Yeah, so hopefully, like if you're doing, so you're using Python, right, Lois?
Yep.
So Python does have a keyword for introducing an anonymous function. It is literally the word lambda.
Yep.
The kind of interesting thing in Python is that the contents of a lambda has to be an expression. And things like if aren't expressions, I think. So the kinds of things that you can do in a lambda are limited compared to a named function. But the one nice thing is that defining a named function is very syntactically light. So Python has map and reduce, and might call reduce fold.
No, I think it is reduce.
Might be. So like you can use them and yeah.
Yeah, no, it's map, reduce, and filter.
Yes. That sounds about right. And see, and Lana, I forget, what language are you using at the moment? Okay. Yeah, with C#, these are delegates, I want to say they're called. And it's the same kind of syntax as JavaScript, where it's the equals less than or greater than arrow. And you use them a lot in LINQ. Which, so in LINQ, map is pronounced select. And then the flat map is select many. And select many, when you're writing C# code, it tends not to be something that you'd explicitly write. But when you write LINQ, a lot of the things that you would write get compiled to a select many. So it's in Scala, C#, F#, Haskell, that sort of thing. A lot of them have some syntactic sugar for calling flat map. So like writing code like this is kind of ugly and a little bit hard to follow, but it's an important enough pattern that there's a more normal looking syntactic sugar. In Haskell, it's called do notation. So you would write like, actually, yeah. So, so in Haskell is a one-liner. I could say something like do a 10 be arrow 1.10 C arrow 1.10, where the 1.10 is like the list of numbers from 1 to 10. It's kind of a nice syntactic sugar for generating large ranges. And then if A times A plus B equals C times C, then C else the empty array. And just, it'll tell us that 3, 4, 5, and 6, 8, 10 are Pythagorean triplets. So those would be the only ones with the numbers less than 10. We could do the same sort of thing with every number under 100. And so if you're doing stuff with right triangles, you can kind of brute force it all. But so in Haskell, you'd usually use the do notation, which usually instead of writing it like this, you'd have it on multiple lines. But the one nice thing is that you can write it in a single line using the semicolons if you're writing it in here. So yeah.
All right, well,
Anything else, or should we call it?
I think we're good. So thank you so much, Elliot, for this lovely presentation that flew over everyone's heads. No.
Sorry about that.
No, that was a good way to look at some different things with functional programming.
Yes. Yeah. So
Thank you.
try to get maybe some hammer in some of the basic examples a bit more. Maybe that might help her. If any of you guys have ideas, hopefully it was still valuable for you guys.
Mm-hmm.
That'd be really interesting. I always think this is cool just to see some, more of the advanced stuff. But at the same time, maybe if we just went through and built something on like a smaller scale, that might be, applying code to build something smaller, that might be interesting to go through, I would say, and applying it. So that would be kind of cool.
So next week, I think, is the immutability one. And one thing I was going to do is there's a language that compiles to JavaScript called Elm. And one of the really cool things that Elm has, so it's for writing like single page app, web pages, that sort of thing. And it has a time traveling debugger, which is to say, because the state of the world is immutable, you can save all of the previous states of the world. And you can also take all of the things that people are, like the input that you're taking in. And so you can see after like you had the button press there, what that did to change the state. So that's actually really helpful to be able to do. And I'll kind of go fairly slowly over that example, I think. That might be a good thing to do. But so it is getting dark, and I should probably try to get the geese inside while I can still see a little something. Actually, Zach, have you been to the farm yet?
No, not yet.
Not yet.
I heard about it at dinner when dinner was still a thing.
Yes.
When dinner was still a thing. Oh.
Well, we still eat dinner, but going to dinner.
Yeah, no, I know what you meant. It's just sad.
The one thing that I have now, since then, is we got 2 geese and 3 ducks that live on the pond.
Oh, nice.
Yeah.
Ducks have the best duck names too.
Yes, well, so the geese are Flapjack and Waffles, and the ducks are Huey, Dewey, and Louie. And
so I'm sure they tell many tales.
Right?
Mostly they like squawk, and like they don't. So I think it's female ducks that quack, and they're all male.
I didn't realize only female ducks quack. I thought just asking if a duck quacks is a standard duck question.
Yeah, I mean, like they make a slightly different sound than like the traditional quack. It's kind of interesting, and they are Pekin ducks. So they're like these gigantic waddling white ducks, and the geese are African geese. So they've got kind of like a white underneath, and then their top is brown. So we got the geese as day-old chicks from the farm store. And then the ducks, someone Sarah knows, had gotten them, and then they couldn't take care of them. So we got 3 of them, and her riding instructor got the other 3.
That's cool.
But
So
yeah.
how do you make sure these ducks don't run away?
They're
Just
inside.
out at the pond.
So we've got some fencing around the pasture that they're in, basically. But for the most part, they stay by the pond and by the coop. One of them has gotten out a couple of times, and that is it. It's actually kind of interesting.
Yeah, I couldn't imagine them being very easy to domesticate, you know. We have some back home in PA. They can fly up to 5-6 blocks away. So
I'm not sure if Peking ducks can fly like that, though. Peking ducks really don't fly as much.
One nice thing about the ones that we have is that they never really learn to fly, for one thing. But more importantly, they're both meat breeds, so they get too big too quickly to really be able to fly well. So they'll flap when they're walking up the ramp into the coop, and that's about it. Or like when you pick them up, they'll start like flapping like crazy. But like the interesting thing is always like getting them up off of the pond, because they'll like swim around like away from where you're trying to chase them, but they won't go up because they're assholes. But the one thing that is super cute is if you're getting day-old geese, they'll like attach themselves to you, and they'll follow you around like their mom. So you can have like a make way for baby ducklings, just like walking around either inside or in the front lawn with like the teeny tiny
Little train.
it's amazing. And like these days they run away from me at night because they know that I'm picking them up to put them away. But like,
Yes, heaven forbid you don't want them to be eaten by a fox.
what was that?
I said, heaven forbid you don't want them to get eaten by a fox or something.
I know, right? Like, they apparently do not want to stay safe.
Ah, what is safety anyways?
True.
But so I should probably head out and take care of that before it gets any darker out there.
All right,
Yes,
it's
good.
nice to hang out with everyone. Have a
Yes.
good night.
Thanks for coming.
Bye.
Yeah, have a great night, everybody. Thank you so much for everything. Appreciate it.
Thanks for coming.
Comment.
See ya next time.
Yep.
Same bat place, same bat time.
Yep.
And that closed that window. It didn't